Well, thanks for the invitation to give a talk. So I'm going to talk in the first part about concentration of measure. And in the second part, I'll talk about applications to graph-based learning. I'm just going to sort of give a slow chalkboard talk where I go over all of the proofs. And please, ask questions if things aren't clear throughout the talk. So our setup is that we have some IID random variables, x1 through xn. And throughout the talk, mu will be the mean value of xi. Sigma squared is the variance. Okay. And concentration of measure refers to bounds on the probability that the sum, which I didn't define yet. So we'll write the sum S sub n, or the average, 1 over n sum of xi. Okay, and so I want some kind of bounds on the probability that the empirical mean differs from the true mean by more than some parameter t. Okay, so I want to know what kind of thing can I put on the right-hand side. And there will be various inequalities that will prove in different situations or different assumptions on the xi's. Okay. So to see what you might expect to get, right, we have the central limit theorem. Okay, so by the central limit theorem, we have an expansion that to first order the mean is the average Sn is just the mean, and the second order correction is sigma, let's say 1 over root n times a normal random variable with mean 0, sigma squared, plus something little o of 1 over root n. Okay. And so if we take the renormalized, say y sub n is root n times Sn minus u, then this thing should look roughly Gaussian. Okay. Which means I should have something like probability that yn is bigger than x is less than a constant, e to the minus x squared over 2 sigma squared. Right? And if I rewrite this in terms of S sub n, so let's say set t is equal to x over root n, I should get something like probability that Sn minus mu is bigger than t goes like exponential of minus, there should be a constant here, minus nt squared over 2 sigma squared. I haven't proved this yet, but this is the kind of thing that we hope to get, right? Okay. So,
for all n,
sir? We will get it for all n in the end. Yeah. Of course, the central limit theorem is only for large n. Right? So before getting into the details, let me just tell you about the applications I have in mind. These kinds of estimates are used sort of in all kinds of different problems, in all kinds of different fields. So the various applications, if you're ever trying to do some analysis of randomized algorithms, this kind of thing will show up. So for instance, Quicksort is one of these. Two, as we saw in Adam's talk earlier today, or yesterday, I guess it was. So these are the sort of the key tools that are used in statistical learning theory. Okay. In the kind of problems that I've been working on a lot recently, which are PDEs or variational problems on graphs, these are the key estimates that you need to control the randomness in the graph. So PDE or variational problems on graphs. And I'll talk mostly about this in the second lecture. But this is not the only application, so I mean, I should mention random matrix theory, because a very big thing recently has been the matrix Bernstein bounds. So random. So we'll prove the scalar Bernstein bounds, but the matrix version have a lot of applications in data science and these kinds of problems. There are some great notes by Joel Trop on the matrix versions of these things. They show up in stochastic homogenization of Hamilton-Jacobi equations, which is exactly the one of the themes of the workshop. So for instance, there's a nice paper recently by Armstrong and Card, let me see if I get this right, Lague, where they prove homogenization for geometric motions, and they have actual quantitative error estimates. And one of the key parts of the proof is being able to control fluctuations in the fronts. And they use the sort of ideas behind the proofs of these concentration and measure results. Okay. So they use essentially Azuma's inequality. Okay. And so I've worked on stuff kind of like this in the past, so these sort of data peeling problems I used to work on, which are sort of like front propagation or something. And the same kind of thing happens here. You have to sort of control the random fluctuations in these fronts, and these kind of concentration and measure things are used here. So I wrote a paper with Charlie Smart on this recently. This is convex peeling. The first, sorry?
You're talking about motion of something like a front normal to itself with some velocity, which is oscillatory.
So in either of these two, I mean, yeah. like in the stochastic homogenization, I think it's something like you could have curvature motion with a bit of noise or something, or I'm not sure exactly what the setting is in this paper, let's say, but it's like this or something. Yeah. And here it's so convex peeling is this algorithm for sorting points into layers by peeling off the vertices of the convex hull. Okay, and so you get this like discrete front propagation. You can prove that in the large data size limit you get, and the layers move by Gauss curvature to the 1 over d plus 1. Okay, and the proof of this uses concentration inequalities to sort of study the analog of the cell problem for the homogenization. So I guess like the first 4 or something, we'll use like the textbook version of these results that I'll prove to you in the lectures. And the last 2 applications are kind of, you have to know the proofs and get your hands dirty and sort of get into the actual details. Okay, so let me, let me just give a few preliminaries that we're going to need. Or I can just, I guess we can jump right into it. So how do you get estimates like this, right? How do you get exponential on the right-hand side? Yeah. So the very first thing you need to know is Markov. So you have Markov's inequality. So if you have a non-negative random variable, so almost surely x is non-negative, the probability that x is bigger than t goes like expectation of x over t. Okay, the very first crude bound you can prove for a tail bound. And the proof of this, if you haven't seen it before, it just goes by writing this as the integral over your probability space of the indicator where x is bigger than t, d mu, where mu is the measure of the random variable. And then you just simply say, okay, on the set where x is bigger than t, 1 is less than x over t. So I can just say less than integral of x over t. Okay. And that right-hand side is exactly this. expectation over t. Okay? So that's the one thing that we'll need from probability. And we'll need to know that some things about independent random variables and stuff. But the surprising thing is that you can prove these estimates with like very, very basic knowledge of probability. There's just some clumsy algebra to go through. So everything goes through this thing called the Chernoff bounding trick. So what you do is you write down what you want, which is probability of Sn minus mu is bigger than t. Okay, and we just prove one-sided bounds. You can prove the other side in the same way. You introduce a new parameter, we'll call it little s. Okay, where this is just some positive parameter, little s. And then you take the exponential on both sides. Okay? This is a monotone function, so the event that this is bigger than that is the same as the event that e to this is bigger than e to this. So probability e to the Sn minus mu bigger than e to the st. Now I have a non-negative random variable here, so I can apply Markov. Right? That's all I'm going to do. Okay, so if I apply Markov, and I can, I'll do it over here. So by Markov inequality, so probability, okay, this is less than, right? So the right-hand side is what I called little t up here, and the left-hand side is the capital X. So it'll be e to the minus st times expectation of e to the little s Sn minus mu. Okay. And the point of this parameter little s is I'm going to later optimize over this parameter. So if I write this out, this is where I have to use some properties of IID random variables. This is expectation of e to the s over n sum xi minus mu. Okay. And so you can write this out. Okay, so first write it as a product. Okay. And then the property that, if I have independent random variables, expectation of xy is the same as expectation of x times expectation of y. If I have an IID sequence, expectations of products can break up into products of expectations. So this becomes product, I is 1 to n, expectation of e to the s over n xi minus mu. Okay. And so this thing has a special name in probability. This is the moment generating function of the random variables, xi. Okay. So write this as, and since they're IID, it's the same moment generating function n times, so it's to the power n. Okay. So this moment generating function mx of lambda is expectation of e to the lambda x minus its mean. Okay. And this is the main thing. So this is the main trick. I go from this thing I want to control to something which depends on this moment generating function. Now, if I can compute this in closed form, I get a nice estimate. Otherwise, I try to get upper bounds on this using only basic properties for the random variables. Questions so far? Now, I forgot the most important. Yeah.
Again, it's left-hand side less than the right-hand side. That's the takeaway from this calculation.
The left-hand side is less than the right-hand side?
Is probability Sn minus mu greater than the t less than right?
Is less than this right-hand side over here, yeah. This is the main Chernoff bounding method. Yeah. The one important thing I forgot is that there's lecture notes for all of this stuff on my website. So if you go to my website, there are calculus of variations notes. Okay. So I'll leave it to you to find them if you just go to my webpage, and there's a link in the front page for calculus of variations, and in chapter 5 you'll find graph-based learning, and there's a whole section on concentration of measure. Okay, so now the question is, when can I bound this moment generating function and get nice results? Okay. So the first thing I'll do are the Turnoff bounds. Okay, these were, I think, some of the first that were derived in this context. So this is the case of Bernoulli trials, where I'm just going to be flipping a coin that has some probability p of being heads, probability 1 minus p of being tails. And so the average Sn is just recording the fraction of heads versus tails. So here I have probability xi is equal to 1 is p. Probability xi is 0 is 1 minus p. In this case, you can explicitly compute the moment generating function. So it's expectation of e to the lambda, and then x. I'll write xi just for a generic one. The expectation of this random variable is just p. Right? So I have that. So pull out the e to the minus lambda p, and then I have expectation of e to the lambda xi. And I can just, there's only two values for xi, 1 or 0. Okay? So it's e to the lambda minus lambda p. And then I have, okay, if xi is equal to 1, that's with probability p, I'll have e to the lambda. And with probability 1 minus p, I'll have just e to the 0, which is 1. That. And it's useful to just get a nice, very short upper bound on this instead of writing that. So we'll use all the time the identity 1 plus x is less than e to the x. Okay. So here, this is my 1, and the rest of the stuff inside here is the x. Okay. So I'll get exponential. I'll have the minus lambda p. And then I have the 1 plus x, so it's going to be, plus p e to the lambda minus p. Okay, everything's right. And let's just stick this. We're going to stick this into the turnoff trick over here. But actually, before we do that, there are two things I want to identify that are very, very useful technical propositions, okay? So just as a quick aside, okay, because we'll use these a lot, if I have a positive delta, this function h of delta, 1 plus delta log 1 plus delta minus delta, this will show up a lot in our computations. And there are two short propositions about this function. So proposition 1 is that it arises as the maximum of the function delta x minus e to the x minus 1 minus x. Okay, h of delta. So you can just compute the location of the maximum. You get this is exactly h of delta. Second, this function is sort of essentially just quadratic when delta is small. Okay? So the second proposition is that if, again, delta is positive, h of delta is bigger than delta squared over 2 times 1 plus delta over 3. And okay, so the first time I saw this, if you look in any book on concentration of measure, they just state this at the end of a proof. Oh, because this is true, I get the end of the result. But actually, like proving this took me like to sit down for like 20, 30 minutes and like figure out how to prove it, because it's not direct. You don't just write down something and it just falls out. So I'll just give you the steps. If you call this f of delta, okay, all you have to do is show that f of 0 is f prime of 0 is 0, and h of 0 is h prime of 0 is 0. And if you check the second derivative of h, it's bigger than, just ever so slightly bigger than the second derivative of f. Okay? And you show these three things, and it's just trivial. And actually, if you plot these two functions, they're amazingly close. This is a very, very good lower bound. You don't lose very much here. Okay, so I have the Chernoff bound, and now I have to do algebra, which I hate doing up on a blackboard in front of people. But these two propositions are going to help us do all the algebra without any kind of without too much challenge. So in the Bernoulli case, right? Okay, this is less than e to the minus st. Actually, let's write it as exponential. And it's moment generating function to the n, but for lambda I have to plug in s over n. Okay. So it's plus n times, now it's minus s over np plus p e to the s over n minus p. Okay, that's my bound. And okay, I could just leave it like that. Say you choose your s, whatever. This is, but this is kind of hard to figure out what's going on, right? So exponential. Let's pull out minus n times p. Okay. And I'm going to have s over n. Actually, no, I'm going to do something else first. Sorry. It turns out that people like to write the Turnoff bounds in a bit of a different way. So this, remember, s sub n is 1 over n, a sum of xi. People like to write things without the 1 over n for the Turnoff bounds, for whatever reason. Okay? So if I just multiply through by n over here, I'll get an n times t on the right-hand side. So I'm going to set delta to be n times t. And then what I have is that probability of sum is bigger than 1 plus delta times np, because the expectation of this mu is just p. Right? This is less than the exponential of the t becomes n delta. Right? And then I get minus s times p. And I get plus n p e to the s over n minus 1. T is delta times n. Yeah. Yeah. So I'm going to multiply both sides of this by n so that I get rid of this n. And then I'll have an n times t on the right-hand side, which I turn into...
You wrote delta equals t, and you mean to write that the other way around?
maybe I meant to write the other way around. Let's see. Yeah. Right, so I'm going to have probability that I is 1 to n xi bigger than n times p plus n times t. I'm going to have that if I just multiply by n on both sides. And so I want to choose, I want t to be p times delta, I guess, right? Sorry. I want t to be, if I choose delta to be t over p, sorry, I got the totally wrong choice for this, right? If I choose t to be p times delta, then I can factor out the n times p, and I have a 1 plus delta, right? So it's t is equal to p times delta. Okay. And okay, thanks. So now I'm going to have, so delta t is equal to p times delta, so minus s p delta, and then minus s times p plus n times p e to the s over n minus 1. I think this is all correct now. Let's see. So pull out the minus n times p, and I'm going to have s over n times delta. Okay. Plus, or I guess minus e to the s over n minus 1 minus minus s over n. So if you do the algebra, this is what you get on the right-hand side. Okay. So why did I do this? Because this function is exactly what I put on the board over there, right, in proposition 1. This is exactly the function delta x minus e to the x minus 1 minus x. I'm going to maximize this over s now. So optimize over s. Okay. And because I have minus here, I want to make this as large as possible on the right-hand side. And that's just going to be exactly h of delta in the end. So I get exponential minus np h of delta. Okay. And you can leave it like this if you like. This is like the most general form for it. But if you want to get something that's, looks like the central limit theorem like we wrote earlier, you want to use proposition 2 to lower bound h. Right. Let's look at that. So if you now use proposition 2, so it's exponential. So it's minus np delta squared divided by 2 times 1 plus delta over 3. Okay, and so that's one form of the Turnoff bounds. You can find, several different forms of these bounds, but here's the one-sided bound from above. Okay, and so it looks like what we expect from the central limit theorem, but the extra delta over here is a bit different. Okay. But if delta is small, you can sort of ignore that term. It looks like minus np delta squared. There's a bound the opposite way, so you also have and the other direction has no extra delta over 3. And of course here you have to restrict deltas, less than 1, bigger than 0. Okay. So because I don't want to just derive these things the whole talk at no end and make it kind of boring, I'm going to give a very simple application of the Turnoff bounds now. So I assume most people have heard of the Quicksort algorithm. Maybe know how it works, maybe not. I don't know. Okay.
Can't remember it.
You can't remember.
Quicksort,
So Quicksort is like it's basically the fastest sorting algorithm out there. It's randomized, okay? And it's only an expectation or with high probability that it works in n log n time, but the worst case is order n squared. But it still is the fastest thing most of the time to do. So the algorithm is if I have a set of points x1 through xn, which are numbers in R, and I want to sort them. Okay. What I do, let's call it QS for quicksort. There's a room here. The quicksort algorithm is recursive and randomized. And we'll have enough space here. I should do it over here. So let's say quicksort. Okay, so what you do is you pick a random point called a pivot. And then you split your data at that pivot to things that are less and things that are greater than it.
Uniformly or
Sorry? What's that?
just uniformly?
Uniformly at random. So it's 1 through n points uniformly at random. Yeah. So then you say x plus is the set x intersect p to infinity, and x minus is the set x intersect negative infinity p. And then you call quicksort on each of these sets. That's it. So you try to, so the ideal thing would be to split in the middle at the median every time. You split it in half each time, and you would split log n times before you split the whole data set. And each iteration takes n operations, you get n log n time. Okay? And it turns out that if you just pick at random, it's almost just as good. Okay? And it's a very simple application of the Turnoff Bounds to prove this. Let me just sketch how this works. Okay? So the way to analyze this algorithm is that you build a tree basically when you do this. You start with your data set x of points, and it splits into x plus and x minus, okay, which can be different sizes depending on where you split. And these split into x, I don't know, minus minus and x minus plus and so on. Right. And eventually, this you stop if you get to a set that has 2 points or 1 point or something, and you know. Yeah. So you have to go through the whole list. So once you pick p at random, to get this, you have to go through the whole list, and you have to check every point if it's less than p or bigger than p, and you put them into either side. So this step here takes order n operations. Okay, and the rest is free, right? Yeah. Okay, so I have a tree I've built here, and it has n leaves. Because I stop once I get to 1 point in that set. And there are n points in total, so I have n leaves at the bottom of the tree. Okay, so I have the depth of the tree, let's call that z. Depth is the number of layers, so this is 3 layers here. Okay, it's not going to be uniform, so some could stop here and some could go on longer. It depends how you split at each step. And so the complexity is order z times n, right? Because every single layer, I have to go through all the points in my data set and sort into either set. So every layer takes n operations, and I have at most z layers. But this is a random variable z. Depends how I split. Okay. Is that clear so far? I just need to show that z is not bigger than log n most of the time, with high probability. Yeah.
Every layer has n most n, but some of them could have less than n.
Yes, absolutely. Yeah. So the very worst case here is that you always select the smallest point p. Okay, or the largest. And so each time you just reduce by 1, and you get n layers, and you take order n squared time. Okay? This is the worst case, but it's extremely unlikely that this happens. Right? So we're going to classify the pivots. The pivots are the points p. We're going to classify them as good or as bad pivots. So it's a good pivot if the number of points, I'll just write bars for number of points in the set. If that number of points here is less than 2/3, and this is less than 2/3. Okay? So I don't split it too far off from half. It doesn't have to be close to half, but just not too far away from half. Okay? And it's a bad pivot otherwise. I now take a path in the tree. So I'm going to start at a leaf of the tree. Maybe this goes down a couple more like that or something. You know, minus, minus, plus, minus, and minus, plus, plus. So take a path from a leaf, say this one, up to the root. Okay, so every leaf has a unique path up to the root of the tree. Okay? And I ask, how many good pivots can I have along the path? Or how many bad pivots can I have? So let P be a path. Okay, so every time I get a good pivot, I reduce the size of my data set by 2/3. Okay? So I can have at most, if I write 2/3 to the k times n, that's how much I reduce my data set by if I had k good pivots. Right? And once that is less than 1, that's it. I'm done. Okay? So from this, you get that you have at most k is equal to, so if you solve for k here, you get log n over log to 3/2. And OK, if you think about this for a second, it's nicer to bound it by 3 times log n. Okay. So you have at most this many good pivots in a path. And so I want to bound the probability of the number of nodes in this path being bigger than a constant log n. So I want to bound probability. Again, I'll write bar p for the number of nodes in this path, so how long it is. I'm going to say for the moment, there's a constant c that I'm going to decide on later. I'm going to bound the probability that the length of the path is bigger than c plus 3 times log n. Okay? And along the path, there are at most 3 log n good pivots. The rest have to be bad pivots. So this implies, this is contained in the set, that the probability that the number of bad pivots, call it y, okay, number of bad pivots is bigger than c log n. Okay, so I just have to bound this probability here. And what's nice is, okay, number of bad pivots. Each time I choose at random, it's a Bernoulli trial if I get a good or a bad pivot. It's probability 1/3 of being good, 2/3 of being bad. Okay. So really, you can write y is a sum of Bernoulli trials. And I can use the Turnoff bounds right here. Exactly. If you're in the middle third, you get a good pivot. If you're in the other 2/3, you have a bad pivot. Okay, so probability of a bad pivot is 2/3. So I can use the Turnoff bounds probability that y is bigger than, now first I'll write it this way, okay? And I'm going to choose, because I have some hindsight to working this out earlier, I'm going to choose delta to be 1/3 here. So take delta as 1/3. I'm not sure if that's because this is also 1/3, and maybe it is, maybe it's not. So I get 4/3. But the n is the number of trials. So it's within these c plus 3 log n trials, I have this many bad pivots. So really, it's c plus 3 log n and times p, and p is equal to 2/3. I'll just put a p for now. And now this is minus n, and so n is again c plus 3, although I have to be kind of careful because it has to be a whole number. So I have to take something between, say, c plus 3 and c plus 2 or something. So I'm going to put c plus 2 log n times p, and divided by, now delta squared gives me a 1/9. And so it's 9 times this is 18, and then this is 10/9. So you get 1/20 in the end if you just work out the algebra. So this is 20. I think 10/9. Yes. Okay, and so now we put in the value for p, so it's 2/3, so that's 8 over 9. And the 2/3 here gives you 30, right? We put in the value for p. Okay, so now I'm going to, I want this to be small on the right-hand side. I'm going to choose it to be 1 over n squared. Okay, which means I'm going to choose my c, so c plus 2 is equal to 60. Okay. I could choose whatever I like here. I can make it better than n squared, okay? But we're going to see why we need n squared in a second. Sorry? I want this whole thing to be 1 over n squared. If I choose, so minus 2 log n is minus log n squared, it becomes 1 over n squared, right? Yeah. If you choose this for c, so c is 58, you check that 8 over 9 c plus 3 is less than c. If you just plug in 58 and check this. So if I put something larger in the left-hand side, it makes the probability smaller, so I can put c in place of all this stuff. So I get probability y is bigger than c log n is less than 1 over n squared. That's what I wanted to bound over here. So this is less than 1 over n squared for that choice of c. So c is equal to 58. But this is just for one path. Okay, so the problem is I have more than one path in this tree, right? I have one path for every leaf in the tree. I have n paths in total. So I had to union bound. Okay, so one thing that we always do in probability is we union bound. This is what probabilists call it, but for us, we're just using that the measure is subadditive, right? So probability of union of a bunch of events is less than the sum of the probability of the events. Okay, this is the famous union bound in probability. So now I want to bound the event that any of the paths are longer than this, and there are n of them in total. So I get n times the probability for one of them. So I get a 1 over n. So the probability that, what is it, z? Right, z. Z is the depth. Probability that z is bigger than c log n is less than n times 1 over n squared. So what we've shown is that with probability 1 minus 1 over n, this algorithm completes in order n log n steps. No, you can do anything you like. It's just, if you really want to be careful and get the absolute smallest constant possible over here, you have to, actually I think you can do better than this. If you look in the books, you can get 20 or something instead of 58. But this is, yeah. Sorry?
So I pick one of the numbers. All right, that's the first number. Then I pick another number, and it's either bigger or smaller than my first one. And I place it to the left or right according to that. Then I pick a third number, and I look where it falls. Right?
Well, no, you sort, yeah.
It's recursive.
That's recursive.
Yeah.
So you do it once, and then each pair gets called again to the algorithm.
Yeah.
Yeah.
So you split the whole data set. When you pick your random pivot, you go through all the points, you check if they're bigger or less, and you swap them in the array until you get them ordered. Right? It takes order n computations. Yeah. Yeah. Well, you don't put them in order. No. You just sort them into, is it less or greater than the pivot? So you're not sorting. You're just going through and checking, is it less than p, bigger than p? Yeah. So we're trying to sort in the end. That's what we want to do. Yeah. We're just this step here is just grouping into two things. Well, it's usually sorted in place. So these steps here, when you split into x plus x minus, you just swap the actual points in the array in place. So when it's done, everything is sorted for you. You don't have to do anything. Yeah. Okay. Let's see.
So just a big picture summary. What you proved was the probability. You're hoping it's log n number of depth,
Yep.
and the bound says probability it's more than 58 log n is 1 over n.
Less than 1 over n.
And
Yeah.
the point is when n is large.
Yeah, exactly. And even though this worst case could be n squared complexity, This basically always runs faster than algorithms that are actually guaranteed to always have n log n complexities. For instance, heap sort algorithm is always n log n complexity. It's not randomized. There's no worst case that's n squared. But this runs faster in practice. And if you call sort in MATLAB, it will do Quicksort, I think. I can't guarantee you for sure. Because the constant is smaller, I think, than other algorithms. So even though lots of things are n log n, I think the constant ends up being smaller in Quicksort than in other algorithms.
So theoretically, it could be worse.
Theoretically, it could be worse, but it's very small probability it's worse, yeah. And if n is small, you don't care, because it's easy to sort when n is small. You only care when n is very large anyways. Right?
So
Okay,
in general,
246.
when people say, okay, this algorithm has, worst case, it's not so good, but generally it's fast. How often can you use those types of bounds to actually prove quantitatively?
I think a lot of times, I mean, I'm not an expert in the field of randomized algorithms or anything, but I think a lot of times people try and do this. I mean, if you look at the analysis on Quicksort in textbooks, they often show expected value of the computation time is n log n. I think this is not so useful because you don't know how often you get n log n versus something much worse. But you want high probability bounds like this. There's a whole book I can point you to that's the point of the book is concentration of measure for analyzing random algorithms. And there's tons of applications in this book. I forget the authors now, sorry. Okay, so this is the turnoff bounds, but even though they're very useful, you can use them in lots of problems, they only apply to Bernoulli random variables, which is very special. I mean, we knew the central limit theorem for Bernoulli random variables a long, long time ago, right? Before we knew it for more general random variables.
So they fail for other ones?
No, it doesn't fail, I just have to prove it to you.
Okay, so it's
Yeah,
true for the
yeah.
general.
The concentration of measure, yeah. Yeah. If you have some conditions, like they have to be bounded random variables or small variance or something, yeah, exactly. I'll show you the different versions, yeah. Okay. So the second one I want to talk about is the Hoeffding inequality. And I meant to keep this in the board, but I forgot to, so I hope I can reproduce it, but this is a thing we got from the Turnoff bounding trick, right? We had this probability is bounded by e to the minus st, moment generating function at s over n raised to the power n. Okay. That's the Turnoff bounding trick. So the next thing I'm going to do is we're going to generalize from Bernoulli random variables to just bounded random variables. Okay. So we use the Hoeffding lemma for this. So assume that my random variables, remember they're IID random variables, xi's. If I subtract the mean, that I'm bounded by a number b, almost surely. Okay. Then I have a bound for the moment generating function. So it's e to the s lambda squared b squared over 2. Okay. And this is how the rest of the arguments go. So we can no longer explicitly compute moment generating functions, but we can get bounds. And bounds are usually good enough. Okay, so the proof uses very basic things, just convexity of the function e to the x. Okay. So I'm going to draw a picture over here somewhere, right here. So here I'm looking at, the moment generating function is expectation of e to the lambda x minus mu. That's what I have. Or for xi, let's call it whatever. So I'm looking at this function e to the lambda x, and I know that the inputs here are bounded between minus b and plus b. Okay, so this function looks like this. So plus b and minus b. And this is e to the lambda x, this function here. All I'm going to use is very basic, right? It lies below its secant line, those 2 points. That's it. Okay. So what's the formula for the secant line, right? I had to actually do some algebra now. So it's the secant line, so e to the lambda x is less than its secant line on that interval. And that's going to be e to the minus b times lambda, right? That's the value over here. Plus, now it's the change in x, right? Which is x plus b. What do I want, right? Change in y over change in x times. Okay, so the slope is e to the b minus e to the minus lambda b over 2 times b. This is my slope, and then if I'm at a point in between, I have my change is x plus b. Okay, so there I did my Calc 1 exercise, the secant line. This is e to the minus lambda b. This thing is just, if we want to write things in a more compact way, this is hyperbolic sine divided by b, right? Lambda b. Okay, that's it. Okay, so I'm just going to plug this directly into here and crunch out the bound. Right? So I have a moment generating function. It's less than expectation. So in place of this, I'm going to put the secant line. So it's e to the minus lambda b plus, and now it's x minus mu, so xi minus mu plus b over v sinh of lambda b. That's it. Now the only randomness is the xi in there, and it's linear. So I can just pull the expectation inside. Expectation of xi is mu, so this stuff just drops out. The b over b cancels out. And I just get e to the minus lambda b plus hyperbolic sine of lambda times b. And actually, if you add hyperbolic sine of lambda b with e to the minus lambda b, you get hyperbolic cosine, right? You need to think about it for a second. So this is hyperbolic cosine lambda b. And then a sort of elementary bound is this is less than lambda squared b squared over 2. Okay. How do you prove this? So this is right up here. Hyperbolic cosine of x is less than e to the x squared over 2. You just compare Taylor series on both sides. And term by term, they're less here than they are over here. Okay. And that's it. That's my Hoeffding lemma. Okay. So this one is a bit easier now. We just plug this into the Turnoff bound, and it's actually easier to optimize here. We don't have to have that complicated proposition from before. Okay, so in this case, okay, I have that probability Sn minus mu. Sorry, there's no absolute values. So it's e to the minus st, and then I have the moment generating function to the n. So I have this bound over here. I have to put s over n in for lambda, and then I raise to the power n, right? So it's plus n times s over n squared and b squared over 2. That's what I get. And OK, so let's just simplify it for a second. So it's s squared b squared over 2n, right? Now we just optimize over s again. And here I can just do it by hand, hopefully. Right? So differentiate in s, you get minus t plus s b squared over n is equal to 0. And so you get that s is equal to t times n over b squared. Right. So I plug everything in. I'm going to have, from this term, I'm going to have minus t squared n over b squared. So minus nt squared And the other term is going to be, let's see, again, nt squared over 2 b squared. So I get minus exponential minus nt squared over 2b squared. Okay. And so this is the Hoeffding inequality. And the only assumption is the one I wrote earlier over here, which is that the difference to the mean value is bounded almost surely by b. Okay. So this is the Hoeffding inequality. And remember, we assumed that xi minus mu is less than b. Okay. So this is great, and so Adam used this one in a lot of his talk yesterday. But there are situations where it's not close to optimal. Okay. So what did we expect to get at the very start of the talk? It was actually exactly this kind of thing on the right-hand side, right? But in place of b squared, we thought we should get sigma squared, the variance, right? Okay, so this is, there can be situations where the variance is similar in size to b squared. Say I had uniform random variables over -1 to 1. I'd have sigma squared as similar size to b squared. This is great. But there are lots of applications, and it shows up in graph-based learning, where the variance is much, much smaller than b squared. And this is a poor estimate. So it's 3:15. Is that right? Yeah. I go to? Okay. Okay, so this is where the Bernstein bounds pick up. So here we actually want to use the variance of the random variables, not just an absolute bound. Okay. So the Hoeffding is, not optimal if sigma squared is much less than b squared. It could be the case that your random variables are concentrated heavily around the origin, but there's some tails that come out to a much larger value to make b very large, but most of the mass is concentrated locally, and the actual variance is quite small. So this is the Bernstein inequality. And here let's write the theorem down first before we prove it this time. We require both the absolute bound and the variance bound. Okay? So if I have xi minus mu is less than b and sigma squared is the variance, then probability that Sn minus mu is bigger than t, this is bounded by exponential of minus nt squared. Now you don't exactly get what you hope, which is 2 sigma squared. Okay? You get this 2 times sigma squared plus bt over 3. Okay. And so you have 2 parameter regimes for this. If t is relatively small, so this guy is less than sigma squared, I can throw it away. It looks like the bound. I want it up to constants. But if t is much larger, and this term dominates, I get e to the minus nt instead. So I get not Gaussian tails, but Laplace tails, so e to the minus t. This is for any t positive. All these things are for any positive t. In almost all applications that I've ever used these kind of results in, I always restrict t's like less than 1 or something. I throw away this term. I care about large n, and I care about good estimates, which have small values for t anyways. Right? I'm going to keep the Chernoff bounding trick up there. Okay, so we have to bound the moment generating function, again, like we did for Hoeffding, but we have to use the variance information as well as the bound. Okay. So this is called the Bernstein lemma. And this is one that I can't remember, so I have to work it out before I write down the actual result. So it's the same conditions that xi minus mu less than b, and sigma squared is variance of xi, and I have some bound mx lambda is less than exponential of, we'll fill the blank in later in a moment. But the trick is really easy for proving this. Okay, so you write down the moment generating function. So it's e to the, or let's, sorry, before doing that, let's just write a bound for e to the lambda x. So I have e to the lambda x. So I'm going to Taylor expand and just pull off the first two terms and write the rest as a series. So 1 plus lambda x plus some k is 2 to infinity of lambda x to the k over k factorial. And I'm going to play a trick where I sort of borrow an x squared from here and then replace it with a b squared or this kind of thing. So let's see if I can write it in one line here. So it's an upper bound, 1 plus lambda x. I pull out an x squared. So k is 2 to infinity. And then what's left, I'm going to have a lambda to the k times x to the k minus 2. And the rest of the x's I'll upper bound by b. Okay? So I'll have lambda to the k, b to the k minus 2 over k factorial for x less than b in absolute value. Right? So I just peeled off an x squared, and the rest of them I bounded by b. And the point is that I want the variance to show up when I take the expectation, and the x squared will give me the variance in the end. Okay. And the last thing I do is I then borrow a copy of b squared and change that back to a k. Okay. Seem okay? X is less than b, yeah. Yeah. X is less than b, okay? So you get e to the lambda x is less than 1 plus lambda x plus x squared over b squared. And what's left here, well, it's just the Taylor series for e to the lambda b minus the first two terms, right? So e to the lambda b minus 1 minus lambda b. Okay. And if I take expectation of this now, expectation of e to the lambda xi minus mu, so that's my moment generating function. And xi minus mu goes in place of x, so it's less than b in absolute value. Well, this term drops out because it's expectation of a linear thing, so it's just mu minus mu. I get this term gives me the variance. And then I get e to the lambda b minus 1 minus lambda b. Okay. That's it. And okay, so here I wrote exponential for the whole thing on the right-hand side. So now we do that silly trick that 1 plus x is less than e to the x. Okay, so this is less than exponential of sigma squared over b squared e to the lambda b minus 1 minus lambda b. Like that. And so that's it. That's what I should put over here. Sigma squared. Okay. Everyone with me so far with this? Okay, so now we just have to plug this in. This is like maybe the messiest one to do. So I have to plug this and put s over n in here and plug it in up there, and then optimize over these parameters. And of course, I erased those propositions from before, right? Okay. Let's start over here.
I think we can trust him.
Yeah, but I don't know what the answer is till I write it down, though, either. But I guess I wrote the answer up here, right? So let's see. Yeah, maybe it's a good idea to to skip a bit of that proof. So right, we have.
Maybe we should raise it.
Yeah, see if you could do it faster. So yeah, you're going to plug this thing in up there, and you get the e to the. I erased. No, it's this thing, right? You get the e to the minus st. You plug in s over n into this, and you raise it to the power n. And so it's sigma squared over b squared. It's e to the lambda b, so e to the s over n b minus 1 minus s over n b. And yeah, maybe I'll leave it here. Now you optimize over s. And here you do use those first two propositions I had before. So if you rewrite this in the right way like we did before, it'll be exactly that function h of delta we had. And you use that lower bound, and you get the Bernstein inequality. Let me stop there. So in the last few minutes, let me just mention a couple of other estimates that are useful. So one is the case of all of these estimates hold for things called U statistics. Okay? And the second thing is the McDermott inequality that Adam talked about, which generalizes this to the case where it's not a sum of random variables, but it's a function of random variables. And as long as it doesn't depend too much on any one of the random variables, you can get the same estimates. Okay? These are both very, very useful inequalities. I think I'll do the U statistic one briefly because it should take a few minutes, and then we'll go pick up with Azuma and McDermott later. So a U statistic, if you haven't taken stats, you wouldn't probably know what this is, and you probably don't care either. But it's a sum where I have, so call it U sub n. So the sum over I is not equal to j of a function of xi and xj, okay? Where the xi's are IID random variables again. And this actually shows up exactly in variational problems in graph-based learning, which is why I want to talk about the inequality. So here f is symmetric. Okay, so I have the expectation, which is jointly over two pairs, xi and xj, where they're not equal, and I have the variance as well. And you get the exact same inequality. So let me just write it down here. I'll just erase the parts that are different. This is Bernstein for U statistics. And yes, so the same thing here, but the variance is different. And this is U sub n. Okay. So probability that U sub n minus this mean is bigger than t. I have to change the 2 to a 6 down here, and that's it. Okay. But the point is that this is actually a different estimate qualitatively, right? Because how many terms do I have in the sum here? I have order n squared. And this is not n squared. This is just n. Okay. So that's because I really only have n sources of independence in the problem, not n squared. Okay? And you can generalize this to kth order U statistics, which is, I have xi, xj, xk, and so on, and they're just all not equal to each other. Okay. How does the proof go? It's essentially the same proof. Okay, let me just sketch two sort of lines of how it starts, and then I'll let you finish the rest of it, or you can look in the notes. So what you do is, this is a very common principle in all these problems, is that if you don't have independence, you try to break things up into chunks that are independent. And then you apply the ideas from that setting. So here I would say, so the proof, define the function v of x1, through x2k. So I fix some k. I define a function on the variables x1 through x2k to be 1 over k times f of x1, x2 plus f of x3, x4 plus f of x2k minus 1, x2k. Okay. And then it takes a bit to work this out, but you can write your U statistic as 1 over n factorial, the sum over permutations, Sn, of Vx tau 1, x tau 2, and so on. X tau tau n. I suppose this is actually a function of all the way up to n, and I just leave out the ones that are between n and between 2k. Okay. And okay, it takes a short exercise to prove you can write it this way, and you choose k. K can be anything less than 2 times n, but you want in the end to be as close to n over 2 as you can. So you want basically 2k to be n. If n is even, just choose k as n over 2. If it's not, take it to be 1 less. Okay? It doesn't matter yet, but at the end of the proof, the larger the k you can choose, the better estimate you get. And it's why you get a 1 over 6 is because you really get like an n over 2 showing up or something. Okay? And the point is you just do this, and then you run the same Chernoff bounding trick on this instead. So you run the Chernoff bounding trick. And the point is that you have basically an average of things, and these things are sums of IID random variables, because you have no overlap between these terms. Okay? So if you take the pairs of random variables x1, x2, x3, x4, and so on, this is a sequence of IID random variables. And so your same method with a Chernoff bounding trick works inside here, and the average doesn't even play a role at all. You're just sort of averaging moment-generated functions for the same types of random variables. Okay, so let me leave the details for you to look in the notes, let's say, and it's a good time to break, I think. Yeah.